Good day, students. Welcome to the third lecture recording on the module Food Proteins. In this section, I will only focus on factors affecting protein denaturation. If we just have to go and recap a little bit on what I actually dwelled on in the recording number 2, I spoke about the phenomenon of the protein structure that is divided into 4 different levels. We had the primary, secondary, tertiary, and quaternary structure, and that's when we spoke about that the tertiary and the quaternary structure gives the protein what we call its native conformation, or the 3-dimensional structure. So when we talk about protein denaturation, we talk about the protein, the tertiary quaternary protein, losing that 3-dimensional structure due to folding, and this folding is usually due to factors that have actually been applied to the protein, especially since all the food that we consume is usually processed. So these are things like your physical and chemicals that are actually added into the food product. So what happens is when the protein is denatured, the structures or the bonds that are affected are the ones that are on the tertiary, quaternary, and secondary structure. So things like your disulfide bridge, your ionic, your hydrophobic interaction, to mention a few, are the ones that are disrupted. However, the primary bond, which is the peptide bond, is not disrupted. So the chemistry way of defining this protein denaturation is that protein denaturation is the changes in molecular structure of a protein without altering the amino acid sequence. So it means that the one and only level that is not affected is the primary structure. When that happens, it's that there is some changes on the protein. Some of the changes are desirable and some are undesirable. And one of those changes that usually take place, the first one being the loss of biological activity. Loss of biological activity, we make an example of a protein. A protein being an enzyme. An enzyme is used to catalyze a reaction. However, if the enzyme becomes denatured by any form of factor, then it won't be able to catalyze the reaction. Other changes would be your physical and functional properties. So it loses some and then gains some. One of the functional properties that the protein that's been denatured can gain or lose is the solubility. Number 1. Number 2, it will also be the structure, the texture, or its physical appearance. Making an example of the egg white that becomes coagulated when it's heated. So physically it changes in terms of texture, and it also changes in terms of color. It becomes opaque. In terms of solubility, what happens in terms of solubility is that your albumins are usually soluble in dilute salt solution or just plain water. But when it becomes coagulated, then it's insoluble in water. So that's when we talk about both the physical and the functional properties actually change. And then one other important aspect is that when the protein has been denatured or unfolded, it improves digestion, because looking at the protein as it is folded. Some of the peptide bonds might be found somewhere lodged within the foldings. So if that protein was actually to be digested as it is in its folded nature, some of those protein peptide bonds would not be accessible. But once it's folded like this, those become exposed, and then the digestive enzymes can actually reach those ones. Okay, so now if we talk about denaturation, then we have to also talk about what causes denaturation. 2 things causes denaturation. It's either they are in physical form or they are chemical form. Physically, temperature does that. Agitation does that. Pressure. And chemically, we have pH, salts, and then we also have reducing sugar. In the next sections, I'll be explaining each and every of those factors. So the first factor is temperature, higher temperature. So what happens in terms of higher temperature? We all know that all food products are processed, and most of the processing that we apply in food products include heating, pasteurization, sterilization, drying, spray drying also. So they bring about some form of the heat. So it means that it will alter the protein in some way. So let's see, how does it go about doing it? So when you apply heat to a food product, or to proteins, or food product that contains proteins, and as we already know that in terms of food products, when we have the ingredients, the proteins is actually, or are amongst a whole lot of different ingredients, your carbohydrates, lipids, and then mostly water. It's not all the time that we work in dry state, we work with water. So by heating, what happens is that when you heat, you increase the kinetic energy, and then what happens is that the molecules that makes up the food tend to vibrate because of the excitement due to increased energy. And then that vibration then leads to disruption of the bonds. And depending on the extent of that heating, if the heating intensity increases, then the bond disruption, the vibration becomes violent, and then it's much easier to disrupt those bonds. So when that happens, the polypeptide that was closely packed now becomes less ordered, because there's change in its quaternary, tertiary, and secondary structure. Of the textbooks that I took some of the information from, they actually mentioned that protein denaturation due to heat starts with the quaternary structure, down to tertiary, and then to secondary, in that order. Okay, so in terms of applying heat, we use a whole range of temperatures in terms of processing, but protein denaturation starts at 45 degrees Celsius. So at that 45 degrees Celsius, when it's applied to a food product, the protein starts to denature. However, if that heat is stopped at that temperature range, then what we call renaturation can take place. When we say renaturation, denaturation is also reversible there. It can revert back to its nativity. So it was a native structure and it becomes denatured or semi-denatured. So if the extent of the heat is stopped, then it can revert back. So that's what we call renaturation, which is reversible. However, in food processing, 45 degrees Celsius does not kill bacteria and most enzymes. So therefore, we actually increase the temperature. So a further increase in the temperature, then denaturation is irreversible. So when that happens, when the temperature increases, what happens is that the protein then starts to precipitate. When it precipitates, some of the proteins lose water binding capacity. So that becomes a negative. That's the change in its chemical structure, resulting in its functioning, whereby it loses water. So that's when we talk about the heat stability, that the protein becomes precipitated because the protein is not stable at that temperature. And what happens in food science and technology, when a protein is discovered, what happens, the first thing that one has to do is to check the denaturation temperature, or what we call the heat stability. So when that protein is highly stable against heat, then we know it's a good protein, because it can withstand those other processing techniques that we apply in food science. So in terms of the proteins that we have, your hydrophilic amino acids are the easiest to denature, and then your hydrophobic amino acids are much more resistant to denaturation than your hydrophilic, but eventually they become denatured. Okay, so in terms of the temperature, as much as we also complain about the loss of water binding capacity, there are some advantages to this protein denaturation due to temperature. One of the advantages is that we use whey proteins, and then they are denatured during spray drying to form milk powder. Like I already mentioned, the egg white becomes coagulated with heat. And then I also mentioned it increases digestibility. Of the most important of the outcomes of denaturation, which is very useful for us as food science and technologies in terms of preservation, is the deactivation of bad enzymes. I mean, we know who the baddies are. We have polyphenol oxidase, we have alkaline phosphatase, and we have other enzymes that are produced by bacteria. So if those enzymes are deactivated, then they won't cause food spoilage. And then lastly, we have deactivation of protease inhibitors, or what we call trypsin inhibitors. These are actually other proteins that prevent trypsin in the stomach, in the pancreas, from actually degrading or digesting our proteins. So it becomes a bad thing, but hey, they become denatured by heat, and then we don't have to worry about them as problematic in our food products. And then secondly, we come to temperature in the form of very low temperatures of freezing. We already know that low temperatures can either be refrigeration or freezing. So we actually talk about the extreme one, which is freezing. So we already know that freezing is one of the most important form of food preservation. And then it helps in terms of longer shelf life, and then the product that is out of season can be frozen so that it can be consumed when it's out of season. Those are all the benefits, okay? However, is that when some food products are stored during freezing, there's this phenomenon called freezing-induced protein denaturation. So it's protein denaturation that takes place due to the fact that the food itself was frozen. Okay, so how does that go about? If we talk about freezing, we have to talk about the three phenomena that happens there. The formation of ice crystals, dehydration, and solid concentration. So when a food product is actually frozen, especially in bad or freezing conditions whereby we have slow freezing, not blast freezing. So there what happens is that slow freezing facilitates the formation of large ice crystals. And large ice crystals are not desirable because what they do is when they form within the food matrices, they puncture the muscles, they puncture the fibers of the food, and in that way they result in texture loss or changes in texture. So that's what happens. Dehydration. So what happens is when this slow freezing is taking place, the freezing starts at the surface of the food on the outside. So it's much faster there, and there's almost nothing or nothing actually happening in the core because it's so slow. So what happens when the surface freezes, then there's what we call an osmosis gradient between the outside and the inside core of the product. So the moisture that is in the middle of the product in the core then migrates from there to the surface because of the gradient. And when it does so, then it forms more ice crystals that puncture the food matrices, and that is known as dehydration. So when that water moves out to go freeze on the surface, it actually leaves the protein and other macromolecules, so it becomes dehydrated. So as a result, what happens is that it destabilizes the fish muscles. Sometimes the dough when it's also frozen. So the dough and the fish muscles become tough because they lose moisture, water binding activity, because the water just migrated. And then you also have what we call solute concentration. These are the salts that were binding water with the protein and all the other macromolecules. But now there's also solute concentration. So the solids concentrate on their own on the side. So that actually leaves the muscle or the body of the food being dehydrated and losing moisture. That phenomenon also takes place when milk is actually frozen. So the caseinate or the casein micelles, which are the proteins in milk, destabilize. And then usually you would look at it and see it as if the milk has coagulated or it's become sour. It forms like globules. It's because of the protein-protein interaction with the water that was frozen. So as much as it's a disadvantage to your fish and your milk, it's an advantage because we all know that when food is frozen and there's some enzymatic activity in there, they become arrested. So your protein, your polyphenol oxidase that will be present in your fruits and vegetables and seafood would actually be arrested in there. The activity will be slowed, so the reaction won't take place. So it becomes a negative and a positive at the same time. And then we come to physical factor, agitation. When you agitate, we cannot go without agitation or some form of agitation in the food. First of all, ingredients are all dry. They have to be mixed together. That's some form of agitation. When you bring in the liquid part of the ingredients, agitation also has to take place. So some form of mechanical shear takes place. It's either you homogenize, you mix, you sonicate, you whip, all those things happen. And when that happens in high protein food, what happens is that the bonds become destabilized. And we know which bonds are this: secondary, tertiary, and quaternary structures. So what happens is that when the whipping is taking place, or the agitation or homogenization, the protein starts to unfold. Like we mentioned, when the protein unfolds, even the hidden hydrophobic bonds are being exposed from where they were hidden. And then when they are exposed, we all know that hydrophobic amino acids want nothing to do with water. So in that instance, when they are exposed, they still want to aggregate on their own. So with the agitation, usually there's air that's being incorporated in the form of bubbles. So what happens is that what the protein does, especially the hydrophobic one, it will then absorb on the air interface, and then on the air side, and then the hydrophilic portion of the protein will want to align to the aqueous side or aqueous phase of the whole food system. So in that way, the protein gets absorbed onto the air liquid interface, because as we already know, hydrophobic groups want nothing to do with water. So they will rather align with the water, and in that way they enfold the gas bubbles in there. And by enfolding the gas bubble, they result in an aerated structure. So an example, when you take your egg white and you whip it, you are allowing the air to come in there, and you are allowing the hydrophobic and hydrophilic proteins to then interact with the different phases in there. So of all the proteins, globular proteins are the ones that's very easy to actually shear than your fibrous ones. Advantages is when agitation or some form of shearing takes place, you then form some food products with newly found textures. First of all, the one that we use is Imana soya beans. Okay, this is top class, not Imana. So, but we all know everything as Imana soya beans. So Imana soya beans is made from soybeans, the protein of soybeans, which gets extruded. When it's extruded, then it changes in the physical appearance and the texture, and the texture then mimics that of meat. Isn't that nice? I mean, I don't know how many years old when I actually realized that when my mom made soy mince, we were not eating real mince. You know what I mean? And then I already mentioned whipping of egg to make foam that's used in making cakes and lemon meringues and whatsoever. Ice cream mix that's being aerated. If there's no air, there's no ice cream. It can't be ice cream. Then it's not nice. And then the same applies the kneading of bread dough when it's being sheared and agitated. And in there, we are developing the gluten elastic structure. So that's your agitation for you. And then we come to the physical factors. To the chemical factors. The chemical factors is whereby we add pH to a food product. So obviously you can't add pH. You have to add acid or base, acid or base, or something that's going to bring about the pH low, reduce it or increase it, either way. So in order for me to explain the chemical factors, what we need to do is we need to go to the next slide where we talk about the amino acid itself. Okay, so an amino acid is an amphoteric molecule because it contains both the positive and the negative. So there can be some changes in charges within itself. It can donate and accept electrons on its own. Okay, so most amino acids are found at neutral pH, and we call that the zwitter ion. The zwitter ion, another one name for the zwitter ion, is what we call isoelectric point. This is the point whereby the pH is, the pH is neutral, yes, and then the net charge on that protein or amino acid is 0. So the number of positive charges is equals to the number of negative charges. Okay, so what usually happens is that each and every protein will have a pH whereby it gets to being a zeta ion. So that is specific for each and every protein, and I mean we have 20 of those. But just illustrating using a simple amino acid, that what happens when you add acid. So when you add acid, you add your hydrogen plus, okay, H plus, your protons, your hydrogen protons. When you add a base by increasing the pH, you add hydroxyl groups. So when adding a proton on a zeta ion, you then protonate the acid group. By protonating the acid group, then you end up with a negative charge of 1. However, if you were to add a base in there, reduce or increase the pH, you then deprotonate the amino group, ending up with a negative charge. So meaning that we can always manipulate the pH of a protein by taking it to its isoelectric point, because at isoelectric point what happens is that the net charge is equals to 0, and when the net charge is equals to 0, what happens is that the protein tends to clot, because there's no charge, there's no repulsion, there's no attraction charge. So the protein clots on its own, and this is a phenomenon that we use in terms of producing your yogurt, because milk has a specific isoelectric point at 4.5. So what happens is that when you are adding your base or acid onto the protein, you then change the tertiary and quaternary structure, because what happens is that there's ionization of the what? You ionize the protein or the amino acid. So that is that. So I'll just make an example of a full protein here. When you add acid and base to a protein, and let's assume maybe this is an enzyme or any type of protein, we know that by protonating and adding hydroxyl group is that you always alter the ionic bonding. Let's go back. Ionic bonding means positive and negative. So this is just a protein structure showing this, the tertiary and secondary. So there are all those interactions that we spoke about. But of the most important two that we're going to talk about is that the pH in food that contains proteins affects the ionic bonding, one, and it also affects the hydrogen bonding of the hydrophilic amino acids with water. So what happens is when you add a hydrogen proton, there's what we call the displacement reaction, whereby this proton then goes to interact or to disrupt the ionic bond, and then it reacts with the oxygen there with the carboxylate ion, and then forms your C double bond OH, your carboxylic group. By doing that, it actually neutralizes the charge here, and then there's no more charge of attraction, because the net charge here now is positive, and then it's positive, so meaning that the amino group does not have anything to bond with. So this interaction here, then this protein on this form starts to unfold, unravel, and open up. As you can see, I'm showing my arrow there, my cursor, that it opens up, and it will also be opening up here. It snaps, because remember, these two bonds are holding this whole strand together. Same applies to when you add a hydroxyl group. It will do the same. It will go to the negatively charged NH3 to make it NH2 with the formation of water. Same applies. This interaction here is also snapped. Number 3, when any of this, whether acid or base, comes to react with the hydrogen bonded side chain amino acids with the water, like here with carboxylic acid, what can happen is, if you bring about the hydroxyl group here, what it does is that it removes this hydrogen and form water and have COO minus. So then there's no more hydrogen to form a bond with the water. So that's what happens. So it affects the ionic and hydrogen bonding. Then we come to another phenomenon known as the ionic strength, whereby when we add ions, or what we call salts. So there are two of those concepts. there's what we call salting in and salting out. Salting in is positive. We want it to happen. It's good for the food. Salting out, not necessarily a phenomenon that's applied in food, but it's relevant in the laboratory and research. So what happens in salting in? Salting in is when you have a dilute salt solution. Dilute salt solution, the textbooks will tell you anything 0.2 molar and less of any salt, whether sodium chloride that's dissolved in water, is a dilute salt solution. So what happens is that when you have that dilute solution, it will then help your proteins to bind water. And this is related to when we are manufacturing meat products, especially cooked meat or processed meat, like your polony, your Viennas, your salamis, and your sausages. So we use brine that's injected into ham, and then to keep it moist. So it's used in the salt in the sausage manufacture. So what actually happens, the chemistry there is that, you know, salt, when it gets into water, it dissociates into sodium chloride, Na plus and Cl minus. So what happens is that when the salt gets there, the protein already has hydrophilic and hydrophobic side chains, and then the hydrophilic ones are actually binding water. Okay. However, then you also get things like your salt bridges, whereby there's protein interaction. So by getting the salts there, you also have a displacement reaction, whereby the salt gets into, like in meat, we have the two protein, actin and myosin. Those are two quaternary structure protein that are working together. So when the salt, sodium chloride, gets into the crevices of the protein, it aligns itself and binds to the charged groups of the proteins of the actin and myosin. So what happens is that it then stops or prevents the protein from interacting more with themselves, and then by interacting with the salt, then the salt helps the protein to bind more water. So we already spoke about the binding, water binding capacity is usually lost with denaturation. However, when the milk has been, not the meat has been injected with a brine solution, the salt helps the protein to bind more water. And especially when the cooking takes place, what happens is that the water forms pockets inside the protein, and that's what brings about the texture of meat and the softness, because it's well hydrated. So it's good. So it helps the water to be bound more by proteins, especially during cooking. Then you don't get a lot of water being lost or oozing out. Okay, in salting out is whereby we use a high concentration of salt. It's not applied in food science. It's applied in the laboratory, biotechnology and biology people, even the food science people that are working in labs for protein purification. So what happens, because of the high concentration of the salt then competes with the water, because there's not enough water for the salt to bind and the protein. So the salt takes up all the water, and then the protein then precipitate out of solution. And that's a phenomenon that's used to actually extract proteins, to get proteins, to purify the protein. So usually they use 75% of ammonium sulfate, but we don't do that in food. And then lastly, we have what we call addition of food additives like your oxidizing and reducing agents. So this is usually applicable in the baking industry, especially where wheat is concerned. The wheat, and we know when we talk about wheat, we're talking about the gluten formation, dough manufacture. So that's bread baking or any form of baking. So what happens is that in baking, depending on the type of product you want to achieve, you can always condition the dough. You can always denature the dough in a way by you will actually get a desired end product. So there's what we call oxidizing agents and reducing agents. So your oxidizing agents, what they do is, when you have, so this is a diagram showing your gluten or your gliadin and glutenin structure of wheat, of your dough. So what happens is that we know in the tertiary structure, this protein is actually, it has a lot of your disulfide bridge linkages. So you can already see the strength of that protein. So what happens is, in baking, what you can do is you can add additives, your oxidizing agents. Oxidizing agents are agents that undergoes reduction. So what these agents do is that they help to dissociate the disulfide linkages. So it breaks down the disulfide bridges, okay? And some of those agents are cysteine and glutathione. So what actually works there is the sulfhydryl group and then the sulfhydryl group on glutathione. So when they're added there, what happens is they result in the dissociation by donating the hydrogen to the what? To the cysteine, okay? And then that is actually reduction. So they donate, and then that results in a more softer structure, not so hard. So what happens is that when you have dissociated the cysteine groups, you end up with a dough that you reduce the mixing time, because remember, the mixing is the dough and the kneading. But when the structure has been softened, you don't need a lot of time to do the mixing, and then it increases its extensibility. So the dough structure has an elastic structure, but then when it's broken, when the disulfide bridges are actually dissociated, it becomes extensible. It can stretch even longer, and that is actually an advantage when you are baking bread, and then you know that carbon dioxide will be produced by the yeast. That's called leavening. And then during proving, then when the carbon dioxide rises, so the structure, the more elastic, extensive structure will allow for the gas being formed in there to aerate the bread and have a good loaf volume. And then also the dough is easy to handle. But then on the other hand, you can also have reducing agents. Reducing agents, what they do is, instead, they do the opposite. What they do is they cross-link the glutenin by forming your disulfide bridges. So what they do is they then oxidize the gluten structure to form your linkages. And in that way, it strengthens the dough, it makes the dough hard, and then it reduces extensibility. So whether you add your reducing agents or your oxidizing agents, that is dependent on the type of end product that you want. But either way, so the agent that is usually used is dihydroascorbic acid, you can already see, which then receives those hydrogen during the oxidation, and then this will then form your strengthened dough that contains cross-linked sulfur or cysteine disulfide bridges. So we are actually done with agents causing denaturation. Lastly, we talk about hydrolysis. Hydrolysis is actually the opposite of condensation. Remember when we said amino acids are joined together to form a peptide bond. And then we said that process can either be called condensation or it can be called polymerization. The opposite of that is hydrolysis. Remember there, water was released as an end product. In hydrolysis, water is added into the protein and then the protein breaks down. The one thing about hydrolysis, it differs from your denaturation in that hydrolysis also actually breaks the primary structure. So hydrolysis is very strong. It can break the strong peptide bond, the covalent bond. So hydrolysis breaks only the peptide bond. It's not worried about the disulfide linkages. No. It is specific for the bond. So then it means it chops down the protein into pieces. So it goes a level lower than your denaturation. So we usually use proteolytic enzymes, or we call them proteases like your pepsin that's found in papaya. Pepsin is my bad. Pepsin is actually found in the stomach, pardon me. We have renin that's found in the stomach of calves, and then we also have trypsin that is also found in the pancreas, between pancreas and stomach. So they are used to break down proteins that we consume each and every day, and then they actually break down the protein structure into simple structure. So it actually causes a large change it results in large changes in structure and obviously function. When the protein is now shorter, what can it do in terms of its biological activities? Okay, so thank you very much for listening to this recording. Wait for the last recording.